Hello and welcome to Bypassing User Account Control, the 29th video as part of our Red Team Fundamentals mini-series. Now, in the last few videos, we discussed how the two fundamental Windows privileges, being SeDebug and SeImpersonate, could be exploited to achieve command execution as the local system account. Now, behind the exploitation techniques we leveraged, user account control or UAC would have inevitably been a roadblock we'd encounter. Now, for the purposes of those videos, we assumed it had already been bypassed. However, assuming isn't enough, as more often than not, the UAC will present itself as a problem during our local privilege escalation efforts. So in this video, we will examine in comprehensive detail what the UAC is, how it impacts access to certain privileges, how to enumerate its aggressiveness, and perhaps most importantly, how we can bypass it. And as always, everything we teach in this video is purely for educational purposes. We accept no responsibility for your actions. Now, to understand why UAC came about and how it functions, before the days of Windows Vista, any elevated change that was made on the system required no verification from the local system administrator. So for example, with Windows XP, if an administrator would have wanted to execute, say, command prompt, that session would run with full administrative privileges by default. And although this might seem valid, given that the user was an administrator after all, this meant that compromising the local administrator account granted complete and unrestrained access over the system. Now, from Windows Vista and Server 2008 onwards, Microsoft decided to implement an additional layer of security called user account control. Essentially, any application that would require administrative rights or access to certain privileges like SeDebug and SeImpersonate would have to go through a consent process known as the elevation prompt. So you would have likely seen this before. If an application requires administrative rights to install it, whenever you launch the application, you'll see that the desktop background becomes dimmed, and then you are prompted the user account control elevation prompt. And from here, you can either select yes to proceed with the installation or no to cancel it. So quite a good security implementation against things like malware, Trojans, and so on. So as you can see, this significantly limits the impact of compromise an adversary can do, having obtained access to an administrative account, because with UAC, no administrative action can be performed until the elevation prompt is successfully met. However, it was not the bulletproof solution that Microsoft may have intended. As with pretty much everything in cybersecurity, there are ways around defensive solutions. Now, at the center of UAC are integrity levels, and fundamentally, they define how much trust a running process has on the system. Now, there are 4 levels by default. You've got low, medium, high, and system. And unless UAC permits beforehand, pretty much every standard user action is conducted using the medium integrity level. Now, obviously, there are situations where low may be used, for example, in browser sandboxing. But for the purposes of this video, we will assume that we are elevating a medium integrity level to a high one. So essentially, any process or any action that is executed by the user will always run using the established integrity level and never a higher one, unless, again, UAC has permitted it beforehand. Now we go into the topic of integrity control in greater detail in our course, but the fundamental aspect to understand here is that privileges such as SeDebug and SeImpersonate are strictly tied to sessions running in high integrity. So if our compromised user account is at an integrity level lower than high, the UAC will prevent us from leveraging those privileges for privilege escalation, as we covered in the previous two videos. So to better illustrate this, you can see we have two implant sessions established in Sliver. Now both of these implant sessions are running under the same user account, but one of those sessions here is running in the integrity level of medium, and then the other is running in the integrity level of high. Now the user under which the implant sessions are running as has been assigned the SeDebug and SeImpersonate privilege, but if you take a look at the implant running under the integrity level of medium and take a look at the privilege column, you'll notice that the privileges don't even show up. Now, if we switch sessions and take a look at the implant running under the process integrity level of high, you'll notice that both the SeDebug privilege and the SeImpersonate privilege now appear, amongst numerous others. I also forgot to mention that if we try to leverage the privileges we have been assigned in a implant session that is running under the integrity level of medium, and so say for instance if we try to use get system to inject into a process that is running under the context of the system account, you'll notice that the attempt of doing so will fail. So as you can see here, we get an access is denied error, even though the privileges have been assigned to us. But then if we changed into the implant session that is running under the integrity level of high, you will notice totally different results because when we execute system, that privilege will be used, and we should shortly receive a system implant session. Now, the level of access granted for standard users compared to administrative ones is slightly different. So standard users who, for example, are not part of the local administrator group but have been assigned privileges such as SeDebug or SeImpersonate will also have to go through an elevation process to acquire a new access token with that privilege assigned, as they're only available in high integrity. But the important point here is not to confuse a standard user executing in high integrity with that equivalent to a session of a local administrator. It's all just a level of privilege separation to ensure that designated user privileges are only used whenever necessary. So to reiterate this point a little bit further, you'll notice that currently our user account, or Smerdova, is not part of the local administrators group. And if we try to launch the command prompt as is, and then execute whoami/priv, you'll notice that even though the privileges, again, have been assigned to us explicitly, they do not appear within the privilege column. It is only until we launch the command prompt requesting elevated rights we get the privileges assigned to us. Now for administrators, however, those users are assigned to access tokens upon logon, and one of those access tokens is an administrative one containing all administrative privileges, and the other is the standard or filtered access token where all administrative privileges are stripped. So for everyday actions such as web browsing, reading emails, etc., the standard access token is used to minimize the impact of potential threats. Only when administrative privileges are required, an administrator can obtain them through an elevation prompt raised by the UAC, at which point they will receive an administrative access token. Now, if any of this is confusing, the fundamental idea is that we want to bypass the UAC to move from a medium integrity level to a high one in order to acquire elevated access. And we do this by bypassing the elevation prompt. And also, just keep in mind that our compromised user account must already be in the local administrators group, as the techniques for bypassing UAC for standard users are slightly different from those for administrators. Now, there are four main levels of UAC each of which appears and behaves differently. Now, most commonly, you will come across level 3, which is the default setting. And whenever UAC is required for things like system-wide changes or the installation of third-party applications, the desktop will appear to dim and present us the elevation prompt. Now, there is also level 1, which disables the UAC entirely, meaning that any administrative action can be performed without any interference. Level 2 is similar to level 3, but it does not dim the desktop. And lastly, level 4, which is the most stringent option, presents a prompt like level 3, but for any change that requires administrative privileges, including settings changes and application installations. Now, most of these levels are usually unchanged on standard workstations, but most commonly you will see level 3. Level 4 has been making its way into organizations with stricter settings, but level 3 balances quite nicely between usability and security. So for the purposes of this video, we will assume that our target is running level 3, though many UAC bypass options work in much of the same way for level 4. Now, we can actually view how the UAC is configured by listing its settings under software, Microsoft Windows, current version, policy system. And the first option here is enable Lua, and this registry value will hold either 0 or 1, where 0 specifies that the UAC is disabled and 1 specifies that it is enabled. And then you've also got ConsentPromptBehaviorAdmin, which holds a value that specifies how the UAC behaves for administrators. And then it's also probably worth mentioning ConsentPromptBehaviorUser, which just controls how the UAC is presented to standard user accounts, that is non-administrators, where the value of 3 will specify that the user needs to specify a set of credentials in order to perform an elevated action, such as leveraging the SeDebug privilege. Now, the main value we want to focus on is ConsentPromptBehaviorAdmin, and there are several different settings for it. So for example, whenever it has a value of 0, it disables the UAC entirely for administrators. Options 1 and 2 control whether a credential or consent prompt is displayed. That is, whether it prompts for credentials or simply displays an allow or deny option. However, the most important option is 5. Now, this option is the default, and for native Windows binaries, elevation occurs automatically without displaying a prompt, meaning that elevation happens in the background. However, for non-Windows binaries, the elevation prompt is presented as usual. Now, one of those properties that controls whether elevation happens in the background is autoElevate. Whenever a binary has this attribute defined in its manifest, and ConsentPromptBehaviorAdmin is set to the value of 5, Windows allows the application to run in a high integrity context without requiring additional confirmation, or more specifically, without requiring an elevation prompt. Now, obviously, not every application can leverage the autoElevate attribute, as that would be a security vulnerability. But in order to do so, it must both be digitally signed by a trusted authority, and it must reside in a trusted directory. So for example, the System32 folder. Now, assuming these requirements are met, then any applicable application that is launched will be launched in a higher integrity level automatically. Now, there are several Windows native binaries that use the autoElevate attribute to automatically elevate its integrity level. You can find them on LOLBAS simply by searching by the technique ID of bypassing user account control. And as you can see here in the binary column, these are all the binaries you can use to bypass the UAC. Now, we're not going to be exploiting any of those binaries within LOLBAS. In fact, we will be exploiting a binary called fodhelper. Now we'll get into why this binary is vulnerable to UAC bypass shortly, but before we do so, we should check that the binary has the autoElevate attribute set in the first place. Now, one of the ways you can do this is by using the sysinternal's sigcheck utility. And for the applications that provide a manifest, it supports the capability of extracting it. And this can be done by using the switch. Now, the utility, unfortunately, does not work with the conventional sliver sideload command. So we're just going to have to upload it. And then to execute it, we can use sliver's execute command with the switch, which will present us the output of the execution and then provide it the path to the binary that we are executing. So because we are executing the binary from the same directory where we are running the command, we'll simply specify sigcheck.exe and then the switch followed by the path to the binary for whose manifest we want to read. Okay, so let's execute this. And then once it's done executing, you'll find its manifest in XML format. Now there are two particular elements we need to focus on here. We've got the requested execution level element, and this just simply specifies the execution level that is required to run the application. So in this case, the level attribute specifies require administrator, and this just simply specifies that the application runs using administrator permissions. And then the other element here is autoElevate. And remember, this just specifies whether the application will attempt to elevate itself automatically without requiring the UAC elevation prompt, which in this case it will, because the value is true. So now we have the first part covered in that we have identified a binary that will automatically attempt to elevate itself to administrator level permissions in order to execute. But we also need to find a way in which we can leverage this specific binary to execute the commands that we desire. So to understand why fodhelper is vulnerable to UAC bypass, within process monitor here, I've defined a filter that monitors for all of its operations. Essentially, it filters down for any processes named fodhelper.exe, whose result is name not found, and whose path begins with HKCU. So I'm going to select OK here, and then using the run dialog here, I'm going to execute fodhelper.exe. And then shortly after, you'll see that the utility launches without presenting a UAC prompt because of that autoElevate attribute we talked about earlier. Now, the particular vulnerability with fodhelper.exe is that it attempts to open up a registry key under MS settings shell open command for which it can't find. Now, even though this registry key is not properly documented by Microsoft, some researchers several years ago found that whatever we specify as the default value under this registry key gets executed by fodhelper. And so because fodhelper.exe gets launched in a high integrity session, theoretically, by specifying a command to execute as part of this registry key, means we can also execute a command alongside it for which will also run in the same context. And fundamentally, that is the vulnerability associated with fodhelper. Okay, so now that we understand the associated vulnerability, we'll need to create the relevant registry key. So to do so, we can use registry create and then specify the hive of HKCU. And then starting with the MS settings registry key, work our way up towards the shell open command registry key. Now, unfortunately, the registry command does not support nested key creation. So this is the way in which we must do so. Okay, so once that's done, we'll need to write a new default value for the registry key. So to do so, we can use registry write. Then we're going to write a new string value, specify the hive of HKCU again, and specify the registry key that we are writing to. And then lastly, the command that we want it to execute. So in this case, we will be using run DLL32 to launch our sliver implant module. Okay, so once that's done, we can select enter. And then to confirm that everything was successfully written to, we can use the registry read command, specifying it the hive of HKCU, and then the registry value that we are reading. And then as you can see here, indeed, our command that we are executing is present. Now within the command registry key, we will have to create a new empty value named delegate execute, as otherwise I found that fodhelper does not execute commands in the way that it's meant to. So again, very simple, use registry write, and since it's a string, we'll specify it of string type under the HKCU registry hive, and then specify the value along with its empty contents. And for it to be empty, you will need a space here, so just bear that in mind. Okay, so with all that complete, we should be able to launch fodhelper, and now it should launch our command alongside it. So to test that theory out, we can use execute along with cmd with the C switch to specify that we are executing a command, and that command is fodhelper.exe. And then you'll see here shortly after we receive a new implant session connection. And now if we list the integrity level of this implant session, indeed you'll see that the exploit worked and we are now executing within the high integrity level. And then from here we can use something like get system to leverage the SeDebug privilege to inject into a system level process to execute under the context of the system account. And so the opportunities from this point are endless. Now, having understood the manual process, which can oftentimes be very time consuming, another way we can achieve UAC bypass is by using a tool called UACMe. Essentially, it groups together numerous UAC bypass methods by abusing the built-in Windows autoElevate backdoor, as it calls it. Now, to use this tool, it's very simple. All you got to do is specify the particular method number or identifier that corresponds to the particular UAC bypass technique, and then obviously the command that is being executed. Now, if you scroll down here a little, you'll find a collapsible called keys. And within this collapsible, you'll find all of the tools supported methods. Now, all of these methods define the particular components for which it targets. And then if the associated bypass technique has been fixed. Now, one of the ways to identify potentially usable techniques is by searching for the techniques that have not yet been fixed. So I'm just going to use Control F here to search for this particular string here. And you'll see that there are several methods that could potentially work for the target operating system. Now, one of these methods, in particular, the method ID of 70, exploits the fodhelper technique that we manually abused. Now, if you are interested in finding out how this particular method works, its implementation details can be found within the provided function. So if we scroll up here and search for the provided function here, you'll notice here that within the shells up source code, you've got all of the functions declarations here. So you can see here it uses several Windows registry APIs to create and populate the relevant registry keys. Now, just before you compile UACMe, just ensure that you have the desktop development with C++ workload. And this will just include several compilers, libraries, and SDKs that is needed to compile UACMe. And then with the workload installed, we can simply clone the repository. And then here, select the release build. And then once done, you can find the compiled executable within its release folder. And then to execute it, pretty straightforward. We simply specify the identifier of the particular technique that we are leveraging. So in this case, 70 points back to fodhelper, and then the particular command that we are executing. So in this case, we are launching our sliver implant module. And then as is indicated by the new implant connection, the technique was indeed successful. And we can confirm this by running get privs on the new implant session. And indeed, as you can now see here, we are executing within a high integrity level. And that concludes our exploration of UAC bypass techniques. I hope you found this video informative. In the next part of our videos, we will transition to Active Directory. And before we take a look at enumerating a domain, and attacking it, we will examine the Kerberos authentication process, as pretty much everything in Active Directory revolves around it. In the meantime, feel free to join our Discord server to stay up to date with us, explore our labs, our latest red teaming course, which covers this mini-series we have been doing so far in much greater detail, and I've left all the relevant links in the description below. Until then, stay safe and I will see you in the next one.